Welcome. So in this video, again, there you learn like contaminant transport, like in a contaminant transport course. But in this video, I just want to give you like a flavor of contaminant transport and how you could use the advection dispersion equation, which we saw like in the previous video, to just solve some simple problem like back of the envelope calculations. Yeah, so that's the objective of this video. Like we're not going to go in detail, and hopefully I will try to keep uh, this as short as I can. Yeah. Uh, okay, so basically, like by the end of this video, you should be able to use like analytical solution of the advection dispersion equation to predict contaminant concentration. So you are giving like what would you be giving? Like you will be like, let's say like a scenario where flow velocity, dispersion coefficient, boundary condition, and initial condition are like defined, and then you solve for the contaminant concentration at a specific point in space and in time, using like 1D uh, 1D or even 2D analytical dispersion equation. Okay, so that's basically like the objective of this thing. So let's start like by initial conditions. So we learned it before about initial condition, and so when we do flow modeling, what we generally do, we start. What would be our initial condition? So our initial condition is that we will run our model in a steady state, take this steady state solution, and use it as our initial condition. Sometimes we do this, yeah. But can we do this with transport model? Can we run our model in a steady state and whatever this steady state solution, we use it as our initial condition? We can't because uh, we need to know the initial concentration of this contaminant before we start the simulation. Was it high? Was it low? Did it exist? It didn't exist. So that information we need to know. Yeah. So in transport model, you need like before you start your simulation, you need to know what was the initial condition of this contaminant. Yeah, that's before you start your simulation. Yeah, and there are many methods like to estimate like this initial condition, uh, uh, or correct like for either to estimate it or to correct like the error in the initial condition. Yeah, but that's again beyond the scope of this course. But I just want you to just be familiar with this. Yeah. Uh, So that's basically here. In addition to initial condition, we also need to know like boundary condition. Yeah. So boundary condition, remember, like there's type 1 boundary condition, type 2 boundary condition, and type 3 boundary condition. So type 1 boundary condition, you specified like value, like you specify the concentration. So you will say like at this boundary, oops, at this boundary, yeah, I have like a specified concentration that is like entering through this boundary. So the concentration at this boundary is constant. So like I have a certain solute, like I have water with, let's say, some contaminant dissolved in it, and this water with this contaminant that is dissolving in it is entering this boundary at a constant. So the concentration of this contaminant that's entering through my boundary in this water is constant. So the concentration of this contaminant will not change. Yeah. Okay. Now this is type 1 boundary condition. Yeah. The you specify the concentration. The second boundary condition is you specify the flux. And sometimes we specify the flux that could be zero, like no flux boundary. So this means that no concentration is entering here, or some concentration is entering here. And like if you want to specify the flux, remember that's similar to when we specified the head, like in the flow modeling, we could also specify the head, and for this like we use like Darcy law. Here, like to specify the flux, you need to like So the concentration will depend on like the velocity and dispersion. And so you need to specify it by like you need to account like in order to specify the flux, you need to account for advection and dispersion. And that's like how so basically like uh, type 2 boundary condition, like you define it like this with like some advection and some dispersion term. Yeah, that's how you will. Versus type 1 boundary condition, you just say, okay, at this boundary, I have this constant concentration, or this concentration that's changing in time, or this concentration that's changing in space. Like you specify it, but here you don't specify the concentration, you specify the flux. The concentration, how is it changing due to advection and dispersion, your flux. Okay, so let's look for 1D analytical solution. Let's just look at some 1D analytical solution for first type boundary condition. First type boundary conditions, these are not very much common in nature. So in nature, you will generally be more like a second type boundary condition, like where, because you can, like in nature, you cannot keep the concentration constant, yeah? But you can do this in a lab. Like if you have in a lab, if you have, let's say, you are doing like a tracer test, like or a column experiment. Like let's say this is like a column in your lab. Yeah. So let's say I have a column here. This is a column in my lab. And let's say I have a tank here. Yeah. Like I put like I have a tank of water here, which is continuously like feeding this column, and then the water gets discharged from here. So in the lab, for example, I could run fresh water through my system. So like because I can, so this is a fresh water that will have zero of my contaminants. So I could like get like the water to go through here, and then like if I'm getting like the breakthrough curve of my contaminant, it will be zero. Yeah, because that's like fresh water. But then I could also like mix the water, like have a water mix, have a good mix it with a contaminant, like say salt, sugar, whatever that is. Yeah, conservative contaminant, and then the concentration will be constant, and then I inject this as a constant rate. So here the water that will be entering through my column here, it will have a constant concentration. So like if I'm having, like if I'm staying here, let's say I made a pulse injection of this contaminant, so now we know that this will advect and spread, like advect and then spread, then advect and then spread. So if I'm getting like a breakthrough curve, like let's say I'm collecting this water sample here and I have a sensor, let's say that will measure, like let's say this contaminant is salt, for example, and I have a sensor will measure electrical conductivity, yeah, where like so water with that's more salty will be more conductive. So how my breakthrough curve will look like? So this is like concentration, and this is time. So at the beginning, like the early arrival, it will be something like this. The most of my pulse will arrive, it will something like this, and then the late arrival will be something like this, and then I get to the background concentration, which is this one. So I can maintain like this constant concentration. uh, I could maintain like this is for a slug injection, but for a continuous injection, like for this, like here, this is for concentration. This is continuous injection, not slug injection. So I could just like maintain like my contaminant here, and then for that case, I could use like this boundary one type condition. So initial condition, like what was my initial condition? At any x here, and at time zero, my concentration was zero. So basically, there was like the background concentration for this contaminant was zero. But what is my boundary condition? Like my boundary condition is that like at x equal to zero, yeah, and at any time I am have a constant concentration. So that's a continuous injection. That's not slug injection. That's a continuous injection. So at any time, like see, I have like C node here. Yeah, this concentration is constant. And then what is my, that's my boundary condition here. What's my boundary condition here? That's like at x equal to infinity, the concentration of that contaminant is zero, yeah, for any time. That's so. What does this mean? This means that I have like, this is called like an infinite boundary. So that's like, so you could have a semi-infinite boundary, like that's a semi-infinite boundary, or you could have like in the positive domain, you can have like also semi-infinite boundary in the negative domain, and you can have like, so, but here this is for like a semi-infinite boundary. Like, okay. So do we have like, so that's my equation. So and to solve this equation, what do we need to do? Like, do you remember? Like, we need to integrate it twice. Yeah. So we need to integrate like this guy, and then like after we integrate this guy, then we will find a relationship between like concentration and distance and time. So basically, at any location here, I could find the at any time I could find the concentration. So can we do this? Yes, we can do this. And the solution for this guy, it looks something like this. Yeah, I mean, so it's like a very like, so if I integrated this guy, I will get like this relationship where I will have the concentration. So this is concentration, like this is C as a function of time and X at any time and any location is equal to like your initial like your boundary concentration, like your uh, C node, like as a concentration, like this entering as a boundary, and then like this error function and this exponential term and this like error function term, and here you have some velocity, here you have some dispersion, like longitudinal dispersion, here you have your time, and so on. This is your length, like where you are, where you want to find this concentration here. So what is this error function? So error function, uh, that's how the error function look like. So basically, let's say for a value like, if like, let's call this b here, like, so this is b, yeah. So if b is equal to 0, then my complementary error function, so b is equal to 0, like this guy is equal to 0, then my complementary error function, then that guy would be equal to 1. So that's like how the error function look like, yeah. But again, so you can check this like from, I don't know if you studied this in calculus 3, like how to do this type of integration. But again, that's again beyond the scope of this course. And usually to do this type of integration, this called like method of images. So I'm not sure if you studied method of images in calculus, but just like you can take my word for this, that like the analytical solution of this guy is this guy, yeah. You can also approximate this analytical solution, so you can basically ignore this term here, because like, why you ignore this term? Because as you move away from your boundary, like this, like the impact of the boundary will not be very much important, yeah. So if you also want to have an approximate solution, especially if you are far away from the boundary, that would be like, you can just like ignore system. Similarly, for type 2 boundary condition, so here type 1 boundary condition, I specify the concentration. Type 2 boundary condition, I specify like is flux, yeah. So concentration, effective velocity, V and T, that's like how you specify the flux. And same, like same initial condition and same like infinite boundary also, like at x equal to infinity, at any t, like the concentration would be equal to 0. And that's what is you expect more in nature. So in nature, let's say you have like a tank here that's leaking, or an accident, like here again, like we are talking about like a continuous injection. So like there is a continuous source that is leaking, and as this source leak, then at your boundary there will be like different fluxes, like there will be like fluxes that is moving at your boundary. Like you need to specify like what would be the flux at your boundary. And so that would be like the type 2 boundary condition, like you specify the flux at your boundary. And does this has an analytical solution? Yes, it has an analytical solution. It looks very much similar to the other one, except that like you get like these, like the other one has a positive sign here, like for type 1 boundary condition. For type 2 boundary condition, you get like this negative sign. And again, like these details are not important, like why this is a positive sign and why this is a negative sign. That is basically because here you need to account like uh, Here, like there is kind of like to account for like this flux, you kind of assume that there is like a negative sink term. So that's like a sink term that will account for the fluxes happening. But again, like these details are not important. Like in the transport modeling course, you will like learn these in details, and like you can spend the whole lecture just to understand, like, or even more than the lecture just to understand this. But to get the story short, like you can also like if you move away from your boundary, you can ignore this term, and that would be like your approximate solution. So that's all what I wanted to show you, that like this guy has a solution, has an analytical solution, and let's solve a problem. That's basically I'm showing you the reason I'm showing you this to you because I want to solve a problem with you. So let's say I think I got this from not from your textbook, from like but this contaminant transport course book of Fetter. I think so. So the Happy Pickle factory makes a pickle at large wooden vats. One of the vats has been leaking brine directly into the water table. The concentration of chloride, so this like saline solution in the brine is like so. That is your concentration, yeah, like in the water. So that's like your concentration, like your initial concentration, yeah, or the concentration that's happening at the boundary, like here, this concentration here. The flow in the aquifer that receives the binary is essentially 1D with the following characteristics. So here we are giving like the hydraulic conductivity, we are giving the hydraulic gradient, so that's like delta H over delta X. We are giving the effective porosity and E, and we are giving the diffusion coefficient, yeah, and that's like m squared over second. And now I'm asking you calculate the concentration of the chloride above the background value at a distance of 150 meter after like half a year. Yeah, so basically I'm telling you what is the concentration, what is C at like 125 meter, and like so what I'm asking you here. C at L equal to 125 meter and time equal to zero point 0.5 year. What is the concentration? Yeah. And again, how can we do this? Well, we have an equation for it. Yeah. So I know I know the concentration of the chloride like that is leaking. So I have a tank here, and this tank is leaking, and the leaking concentration that is given here, which is this guy here. So I know this guy. Then I look at this equation. L is giving, yeah, L is like 125 meter. T is giving, like this is 0.5 year. I need to convert this to second, yeah. Uh, this guy, like this guy is not giving. So I need to calculate this guy. So what is this guy? So this guy is like the dispersion times the velocity times the diffusion coefficient. What is this like a dispersivity? Like so dispersivity, you can use this equation of longitudinal dispersivity. So to calculate like this longitudinal dispersivity, like this, you can use this equation to calculate like your longitudinal dispersivity. Yeah. And again, like this longitudinal dispersivity, you can also estimate it from a tracer test or from like as one of your modeling parameter. But here to calculate dispersivity, like this equation is giving. Now velocity, like how do we get velocity? So velocity, we know this, yeah? We know that velocity is equal to, remember like Darcy law, like Q is equal to negative Ki, and then velocity is equal to Q over NE. So that's basically what we have here. So that is like velocity, that's K, hydraulic conductivity is giving, porosity, effective porosity is giving, hydraulic gradient is given. So that's like this guy here, this is like this guy here, this is like this guy here. So I can calculate my velocity here. And then what else? And I think that's it. Yeah. And here's just like this is this guy here. This is this guy here. So I think that's it. And now one thing, like how can we calculate this error function? So there are like you can do this with your calculator. I think your calculator can do this. You can do this with Excel, you can do this with Python, you can do this. There are tables also for this one. So let me show you like uh, uh, so like this is like so this is the error function, and this is here, this is called like complementary error function, and complementary error function 1 minus error function, and that's like how you calculate like your error function. But you can let me show you what I have here. So I solved this problem for you, and I'm giving you a homework problem that is also similar to this one. Let's see here where it is. Let me try to find my solution. Should have prepared this lessons. Okay, hopefully I will end this video like in less than half an hour. Okay, so let's look at my solution here. So this is my concentration, like this is my concentration of the brine in the water. This is the hydraulic conductivity. This is the hydraulic gradient, effective porosity, diffusion coefficient. This is where I want to find like a distance of 125 meter. This is the time, like half a year. I convert this to seconds. So these are my input parameter, yeah? And then that's what I want to calculate. I want to calculate like dispersivity. And dispersivity, that's like giving like log L. So basically, here, this is the log of L to the power of this one. And then I need to calculate my seepage velocity, and we have an equation for this. So that's basically will include your hydraulic conductivity, your gradient, your effective porosity. And then once I have like these two guys, then I can calculate my the and you can feel like to make this here. Okay, that's your Vx. Then I can calculate my dispersion coefficient. And my dispersion coefficient, that would be basically like this guy times this guy plus this guy. But like, see, that's what I was telling you before. Like, see, this is 10 to the power minus 5. This is 10 to the power minus 9. So basically, this is 0. I could just ignore this. Like, if I, like, see here, if I didn't, uh, like, if I didn't put this guy, I would just get the same number. Yeah. Because see here, with or without like this diffusion coefficient. So basically you can ignore this and just like you can, most of your dispersion is occurring due to spreading, not due to regular diffusion, because that's very small, 10 to the power minus 9. Here's this is 10 to the power minus 5. Okay, and then now I have everything. I just need to calculate like this error function, like this term, this term, this term. So what I did here, I'm doing it to you step by step. Like, so I have this L minus VXT, and I have L here plus VXT. So I call this like B minus like for this term, and I called like this B plus for like this term here. I'm just calculating them one by one, yeah. So if I calculate it, so like this B plus, that would be what? That would be L minus VXT. That's like L minus VXT divided by 2 square root DLT. Yeah, so if I calculated like this guy here, I will get this number. And if I calculated like this guy here, I will get this number. And now let's look here. So that's like almost zero or very close to zero. So like, so at zero, what would be my complementary error function? It would be something close to one. It's a little bit less than zero, so I might get 0.9 or something here. And for this one, that is almost like, if you look here, that would be very like, that's like 5. So that would be somewhere here. So that's almost close to 0. So like for this second the term here, that would be something, yeah. So for my first term, I got something close to 1 because I'm here. For my second term, like this one, I got something close to 0. Like, see, for like the error function here. But then, like, if I calculated my exponent here, I get something, because like that's like I get something, and then I can calculate the exact solution. So the exact solution, basically, I will account for like this term and this term here. And if I did the exact solutions, the concentrations that I get, so after half a year at a distance of about 125 meter, the concentrations that I will get would be about 628 milligram per liter. Uh, that's the exact solution. If I did the approximate solution, that would be around like, which is only like this term, like I ignore this term, like it's not very different, like it's something close, yeah. You got like something close, yeah. Because like the further you go away from the boundary, the further the impact of the boundary will not be important. Okay, so you can, so that's like basically how to solve this problem, and I think you will have a homework problem similar to this one. So here, that's just what I showed you. You first calculate your seepage velocity, you estimate your hydrodynamic dispersion, you express time in second, and then you substitute here. So that would be like what I got here. And for this, I got like this concentration. And then if I want to, the approximate solution, so I can ignore this term, and then that's what I got for this concentration. Yeah, is it the same? Let me see if I make. Yeah, 714. Yeah, 628. Yeah, some very similar. Yeah, so I got something that is very similar. Okay. Now, this is just one example of an analytical solution where, like, so what I showed you, like, this is the solutions that I showed you is 1D continuous. So the solution was like for 1D, like it's a continuous because this, like, VAT, for example, is continuously injecting this, like, contaminant for type 2 boundary condition, like we did this for type 2 boundary conditions, this example. But again, like I showed you also the solution for type 1 boundary condition, and there is solution for type 3 boundary condition, and there are solutions for continuous and slug injection. Slug injection is just one time. Continuous means that this concentration is continuously, like you have a continuous source. There's this time. Slug means one time source. This is like a continuous source. But for 2D, there is also analytical solution for 2D, like point sources. Like if you have a point source, whether like an instantaneous or continuous, in a uniform flow field. So if you have a point source and uniform control field, you can also find like a 2D solution. Like so that would be the concentration not only at X but X and Y. Yeah. Uh, Analytical solution there could also account for additional processes, like they could account for like linear absorption or like first order decay. Like if you have like a reaction like a first order decay or a linear absorption, there are also analytical solution for this. So they are very useful to make back of the envelope calculation. Yeah, these analytical solution. And remember, when we talked about modeling, I told you sometimes you can do just some hand calculation just to confirm your modeling results. These are the hand calculations that you can do just to confirm your modeling result. Again, they're not going to be the same, but they will give you an idea. Am I on the same order of magnitude? Yeah. Uh, Analytical solutions are generally not available for complex like real world scenario. Like heterogeneous media, for example, like variable flow, like your flow is changing, like complex geometry, or like non like complex geometry at your boundary, or complex boundary like condition, or like non-linear reactions, for example. And for this like real world scenario, what we generally do is that we will generally use a transport model. And I showed you an example, like a quick example. Remember when I showed you this case study, this like remediation case study, and from this remediation case study, what did we do? Like we wanted to simulate different contaminants, like we had like 12 or 15 or 20 of them, and we wanted to simulate like different contaminant. And for this, we use something called like MT3D. Yeah. So that's like what we use for this. Like we use MT3D, MS to simulate this different contaminant. Yeah, but there are other like the software, like and these are like this called like MudFlow family, because these are compatible with MudFlow. So from MudFlow, what do you do? Like from MudFlow, you calculate the H, and from the H you calculate the V, and the V you input it to your equation here, and then for pH 3D, this has very like detailed like reactions to it. RT, like this reactive transport 3D. CWAT, that's again another Mudflow family software, and that one is generally used for like CWAT, that is generally used for what? Like the CWAT that is generally used for density dependent flow, like salt water intrusion and things like that, like when you have like a chloride transport, like a density dependent flow. So that's mainly we use this to model like salt water intrusion and things like that. But again, uh, that would be a separate course. So one separate course would be about like a contaminant transport, where you learn like this contaminant transport processes in detail. You learn about different types of reactions. That's one course. Second course would be react like transport modeling. So that would be a second course, like transport modeling, where you learn how to use these software, like you learn how to use something. So this basically like fast 3Ds, I think that's a combination of MT 3D MS and something called FreakC, which is like detailed uh, hydrogeochemical reactions. So like you learn this in so like for example, like I did my master in groundwater hydrology, and uh, we had like just one course like to about like flow modeling, and another course about transport modeling, and the third course about like reactive transport modeling. And in addition, we have one course about transport like flow, and another course about like transport. Yeah. So that's like it was like 4 or 5 courses. Like I learned this in 4 or 5 courses. But here I'm just like trying to give you a flavor so that you'll be familiar with it and that you will at least be able to solve this simple problem. So I think that's all for this module. And yeah, if you like this material, consider taking the contaminant transport course. Okay, so that's it, and see you